Hello everyone, my name is Chirag Sharma and my RIC topic is Stateful Distributed Firewall with Deep Packet Inspection in SDN Networks. So let's get started and take a look at. So let's get started with the introduction and we're going to answer why we are using SDN and why it is an emerging technology and what are bottlenecks that are faced in today's SDN network solutions. So as you can see in the architecture, the control plane and the data plane are separated, in which the data plane consists of the programmable switches which are dumb, and the network controller, the control plane has all the controlling logic, that is forwarding, flow rule updation, conflict policy, conflict management, and it has a global view of the entire network, and on this we can build applications such as firewalls, deep packet inspection modules, and other stuff like load balancers, etc. So SDN has been promising, and it has shows great results in vertically integrated networks such as cloud, which address the issues such as scalability, reliability, and latency. But due to the separation of the control plane, and there is no straight tracking mechanism on data plane, uh, as a result, the SDN controller becomes overwhelmed when there is a large volume of traffic heading towards the controller for the packet analysis, for the header verification, packet header verification. So this can be a performance bottleneck, and can the controller can be susceptible to the DOS attacks and DNS amplification attacks. The reason for this is the reason for stateless and centralized nature of these firewalls in open is the open flow protocol, because that does not allow the adaptive straight tracking of the TCP packets. Moreover, there is a lack of the application layer protocol classification at the data plane level. So each and every packet, like HTTP, FTP, has to go through the controller for payload analysis. Let's take a look at stateless and stateful forwarding in SDN. The stateless data plane model, the controller has to do everything like maintaining the global as well as local states of the packets. So as a result, it becomes very cumbersome task for the controller to to read every packet, to do the analysis of the packet, to do flow rule updation, conflict resolution, etc. So suppose if there is a large volume of traffic heading for the payload analysis and the checking the headers and etc. So controller will be overwhelmed in this case, and this would be a performance bottleneck. So a solution to this is stateful data plane model, in which the switch is smart, in which the switch maintains the states of the packets, the such as stateful protocols such as TCP, which has states sin, SYNAC, and ACK, and these are very useful for monitoring the TCP SYN flood, DNS amplification attacks, and the other DOS attacks, etc. So what happens in traditional the SDN network is that it caters only for the north-south traffic. So once the attacker is breaks in into the network, it can traverse to any node and n number of nodes, which is again a bottleneck in case of security. Now, our proposed solution is that the traffic, according to its states and according to its behavior, should be filtered at the switch level only. So there should be a decrease in the controller overhead, and the controller should only intervene in case of any open. So let's take a look at the solution of distributed stateful forwarding at data plane. So how we're going to implement the stateful forwarding at data plane. We'll use the regular open flow rules, the basic open flow rule installation on the our open switches, along with the OVS contract module, which has some extended fields, which can help maintaining the state of the packets. So packets can be tracked by assigning the flag value to CT underscore state field, such as the value of this field can be new, EST, REL, RPL, TRK, and each of the flag is accompanied with plus or minus sign, which tells whether the flag is set or unset by the contract module. For example, if there is a new packet that is entering into the switch, the flow rule will mark it as the minus TRK, which means that the packet is untracked and it has not been passed through contract module. Therefore, it is value is minus, and TRK means it is untracked. And below is the open flow rule example, in which it says that to add a flow on the particular OVS bridge, in which we assign the CT state as minus TRK, we assign the protocol as TCP and the ingress port, and we set the action as the committing the first open flow rule into the contract module. So let's take a look at the architecture for implementing the distributed stateful forwarding solution. In this, our open flow table will consist of the CTs underscore state field, which will assign flags such as plus new, minus TRK, plus EST to monitor a three-way TCP handshake. And this open flow table will be committed into the contract module. And the contract module will further dump it into a CT table, that is contract table. So our local event listener, which will be written in Python using the Flask API, can track these events and can monitor these events occurring in the CT table or updating in the CT table to monitor whether this is a normal TCP handshake or it is showing some attack pattern or like a TCP SYN flood or some other state related attacks. The event listener can intervene and update the flows to drop the packets in case of such attack scenarios without the intervention of the controller. So this will reduce the controller overhead. And our event listener can be implemented on the OVS itself with the help of the Python using the Flask API and deployed as a REST API. So let's take a look at the TCP SYN flood attack and how our proposed solution is gonna help in mitigating the TCP SYN flood attack. So a SYN flood packet into our open vSwitch, and our open flow rule is such that the CT underscore state equal to minus TRK will set the packet to untracked, and it will be committed to the contract module where it will start tracking, and from there our event listener will check for the events happening inside the CT table, and it checks that the number of new packets are 100, whereas there are no established packets corresponding to it, which means that the host has sent only SYN packet, and now it's time for our SYNAC to be sent from our side. So there is no flow modification due to the because there is no the ratio has not increased to the threshold value. So now again, instead of ACK sending from the host, it again sends the SYN packets in a large volume. Therefore again it goes on with the same process into the CT table, and the event listener reads it, then updates the number of new packets to 200. So again, there are no new established packets or acknowledgements from the attacker or the malicious host. Now since the threshold value, the ratio has crossed the threshold value, so now the flow modification will take place, and the event listener will update the open flow rule, and will and the any more SYN packets will be dropped from the malicious host. So let's talk about integrating DPI into our proposed solution onto the data plane, as this is the novelty step of our proposed solution. So let's get started with it. So contract module also has one more field for classification of layer 7 protocols such as FTP, SMTP, SIP, etc., which is CT underscore mark. With the help of city underscore mark, we can classify the traffic and then we can send it to the DPI module with the help of service function chaining mechanism, which is the concept of SDN. In this case, our open vSwitch will become the service function forwarder, which will be configured on the SFC agent implemented on the northbound API of the SDN controller. Let's take a look at the example flow that we have written here. So it says that add a flow with having ct underscore mark. This contains the hex value which represents SSH. So the flow will send the packet classified as SSH to the SFC agent through our service function forwarder with the toss value of 136, which signifies the 4-bit DSCP value, and the path ID of the rendered service paths, which in our case is the DPI service, which has the path ID of 34. And the DPI module is already implemented on our SDN controller as a REST service. So now we're gonna discuss about our OpenFlow vSwitch rule set hierarchy. So what all rules we are gonna install on our OpenFlow vSwitches for packet state maintenance, layer 7 classification, and sending layer 7 classified packets to DPI module for payload analysis. So our first flow table will be to connect to or to attach a contract module to each and every packet to for their packet state maintenance, and the contract module will be monitored by our local state event listener, which will monitor the traffic patterns of TCP, SYN flood attacks, other state related attacks. And then this table will also be the flow table 0 will also be committed to the flow table 1 in case there is any L7 classification required. So the flow table 1 will resubmit to table 2 once it has classified the data to whether this is a SSH packet or a BitTorrent packet or an HTTP packet or a Facebook, YouTube, separating this according to the DSCP value assigned to it. Then we'll send the each and every packet to DPI module in case of the payload analysis. So the flow table 1 and flow table 2 will be handled by the service function chaining agent, SFC. The SFF, the flow table 1 and flow table 2 will be installed on the our OVS, which is our SFF. So SFF will forward it to the SFC agent, and SFC agent through the rendered service path will send the packets to the our DPI module, which is implemented on the SDN controller. So that is all for this research proposal. Thank you. Messages such as topology management, load balancing, and that kind of stuff. So this caters to the east-west traffic in which if a node is compromised, so the attacker may not be able to traverse to the other nodes through our proposed solution.